acid and base strength versus conjugate base and conjugate acid strength. Strong acids. Let's go over some of their characteristics. They are better proton donors than weak acids. Therefore, strong acids have weaker conjugate bases. Their conjugate bases have less affinity for a proton. Let's go over to weak acids. Weak acids are poorer proton donors than strong acids. Conversely, weak acids have stronger conjugate bases. Their conjugate bases have stronger affinities for a proton. We're going to show that in equation form on the next slide, but notice we're using the Bronsted-Lowry definition here for the acid and the base, right? Because we're talking about protons moving. Consider the strong acid hydrochloric acid, HCl. Here's the acid. Over here is its conjugate base, right? Because it loses the hydrogen, it donates it. This will be a weak conjugate base. Now we have the weak acid hydrochloric acid. And a while ago we talked about why that was a weak acid. Well, here it is. It's a weak acid because it has a strong bond and so does not dissociate to the same extent as these guys. Hydrochloric, hydrobromic, and hydroiodic. So, because this is a weak acid, it will have a stronger conjugate base when it gives up its H+ ion. We have our hydrochloric acid, a strong acid, and we tell that chlorine here is a weak conjugate base because that has almost no tendency at all to accept a proton from the hydronium ion over here. When I have the weak acid hydrofluoric acid, it has fluorine here, which has a stronger tendency to accept a proton from the hydronium ion. Chemists have developed rankings on how well acids donate a proton to a water molecule. There'll be a diagram on the next slide, but first let's say it in words. As acid strength decreases, conjugate base strength increases, kind of like an inverse thing here. And here's the word inverse. There is an inverse relationship between acid strength and conjugate base strength. As base strength increases, the conjugate acid strength decreases. Once again, there's an inverse relationship between base strength and conjugate acid strength. Here's our handy diagram. It actually looks like two pieces of litmus paper, doesn't it? We'll talk about that later. Any acid above hydronium plus is a strong acid. Here's your strong acids up here, and you get weak or go in the other direction. Strong acids means you're 100% ionized in water. As acid strength increases, the conjugate base strength decreases. So here, this is a very weak base. Here's the strong acid. Here's its conjugate base. And notice the base strength increases going down this way. Any base below and including the hydroxide ion is a strong base. And down here, you are 100% protonated, how about that word, in water. Strong acids completely dissociate in aqueous solution. It's these guys up here. Their conjugate bases are very weak. In the middle of the diagram, represented by that oval, we have weak acids partially dissociating in aqueous solutions. Their conjugate bases are weak bases. Strong bases now, at the bottom of the chart here, readily accept a proton from an acid. They get protonated. Their conjugate acids, over here, are very weak. We now want to predict the direction of an acid-base reaction. So using the tabulated data, which we've shown on the previous few slides, we can predict the direction of an acid-base reaction. The key is that a stronger acid and a stronger base will always react to give a weaker base and a weaker acid. So here's example 1. Predict whether the forward or reverse reaction is favored for this reaction. And we'll do that on the next slide. There is a 4-step process to figure out which way this reaction will go. So the first one, step 1, identify the acids. Hydronium and carbonic acid. Why? Because they each give up a hydrogen, right? Because if you go to the forward, this turns into water, gave up a hydrogen. If you go this way, this gives up a hydrogen to form hydrogen carbonate. So we have the acids. Which is the stronger acid? Please look at the chart and write that down. Okay, I'm not going to do it here. I'm going to wait till we pull out the answer. Now identify the bases. Well, here's a base, hydrogen carbonate, and here's the other base, right? Because they each accept a hydrogen going in the opposite direction. Look at their base ranking. Use the table from the previous slides, and which is the stronger base. Remembering the key to solving this problem is a stronger acid and a stronger base will always react to give a weaker base and a weaker acid. So take a few seconds to come up with your answer, and then we will pull out the answer tab. Okay, here we go. As we said, hydronium is a stronger acid than carbonic acid. It's higher on the list from our chart. Hydrogen carbonate is a stronger base than water. It is lower on the list. Therefore, the reaction will proceed in the forward direction as written. So that means it's going this way. Predict whether the forward or reverse reaction is favored for this reaction. We have acetic acid, sulfate ion, forming acetate and sulfuric acid. So step 1, identify the acids. Well, we've done that in red. These are the acids. Which one is stronger? Is acetic acid or sulfuric acid stronger? And then there's a little consulting being done here. Sometimes this guy is written as this, and acetate is written as this. Okay, so you'll have to look that up on the table. Next, identify the bases. And we've done that in blue, right? Sulfate and acetate. Which one is stronger? So please work that out, and we'll get to the answer tab in a second. You can pause the video if you'd like. And here comes the answer tab. And let me erase our colors there. Sulfuric acid is a stronger acid than acetic acid. It is higher on the list. Acetate is a stronger base than sulfate. It is lower on the list. So in this case, the reaction will be going backwards. So let's go ahead, put the arrow in. That's the direction of the reaction. It's a reverse reaction. There's another way to classify acids as strong or weak. It involves determining the size of the acid dissociation constant for a reaction. We've already shown the general structure of an acid is this. H and A are the ions that dissociate when the acid dissolves in water. Here's the general equation. Okay, and this can either be a solid or a gas. Here's water. This shows that the reaction goes both ways. And the equilibrium expression will be written as follows. And there'll be a whole unit on kinetics and equilibrium coming up. The brackets there mean the molar concentration, and Ka will be the acid dissociation constant, and there's the square brackets again, molar concentration. We usually omit the units. Now just look at this little notation here. You saw the colon and then the negative up here. That's not a bad smiley face. That means it's an anion with a lone pair of electrons. The colon there, and I'll put it up here, that's the lone pair of electrons. Depending on the order your teacher goes, you're either going to be recalling from the equilibrium unit or you're going to cover that next. But so we'll just give you a little hint here. Pure solids and liquids are not included in equilibrium expressions. So equation 1 can be simplified to give equation 2. Here's equation 1. And water is a pure liquid, so we don't put it over here. Okay, see right over here. Pure solids and liquids are not included. Strong acids completely dissociate in water to ionic products. Their acid dissociation constants, therefore, are very large because products predominate over reactants. Weak acids only partially dissociate in water to form ionic products. Their acid dissociation constants are smaller compared to strong acids. So here we go. Weak acids have a range of K sub A values. The stronger the weak acid, the larger the K sub A value. Always good to have a table to illustrate what we just talked about. Here are various acids. Here's a formula. And then over here are their dissociation constants. Notice hydrochloric acid, which is very strong, has a large Ka. Hydronium, which is kind of on the border between weak and strong, is at 1. And then look at the range of the weak acids. From 10 to the minus 3 all the way down to, well, small. Small must mean less than 10 to the minus 14. So there's a clear difference there between strong and weak acids. A couple of examples for you to work. One, which is the stronger acid, phosphoric acid or acetic acid, and which has the higher acid dissociation constant, phosphoric acid or hydrofluoric acid. We're actually asking the same thing here. So the stronger acid has the higher acid dissociation constant. So go back and look at the table and come on back. You can pause this and we'll pull the answer out in a second. And here we go. In both cases, phosphoric acid is the answer.